Ancient engineers built ships that crossed oceans without a single nail. They assembled massive, seaworthy vessels using only wood, rope, and a deep understanding of natural forces. By the end of this journey, you will understand the brilliant system that made this possible, a secret hidden in plain sight for thousands of years. How did they bind planks so tightly that the hull could flex with the waves? What was the mysterious waterproofing agent that sealed their seams? The answers reveal a philosophy of engineering that modern builders are only now beginning to appreciate. What does it truly mean to build something that lasts? The heart of ancient Egypt beat to the rhythm of the Nile. This was not just a river, it was a sprawling, liquid highway that connected the entire kingdom. Without it, the civilization we know simply could not have existed. Think of the immense stone blocks needed for the pyramids at Giza. They were quarried hundreds of miles away. How did they travel such a vast distance? They sailed. The Nile was the only conveyor belt capable of moving these monumental weights, but it was more than just a transport route for grand monuments. It was the central artery for daily life. Food, pottery, linen, and papyrus all moved along its currents. Trade with distant lands depended entirely on vessels that could navigate not only the calm Nile, but also the open waters of the Mediterranean and the Red Sea. This absolute dependency created a powerful engine for innovation. Metal, particularly the copper and bronze needed for nails, was scarce, expensive, and often reserved for weapons and sacred objects. So Egyptian shipwrights faced a brilliant challenge. How do you build a strong, reliable, and massive boat when you cannot rely on metal to hold it together? Their answer was not born from a lack of technology, but from a profound understanding of the materials they had in abundance. They looked to the river itself, to the reeds growing on its banks, and to the trees in its fertile valley, and they devised a way to build that turned a limitation into a legendary strength. The proof of their genius lay hidden in the sand for 45 centuries. Sealed in limestone pits at the foot of the Great Pyramid of Giza were the ultimate time capsules, the solar boats. These were not mere models or symbolic offerings. They were fully functional, majestic vessels, carefully disassembled and buried for the pharaoh Khufu to sail with the sun god in the afterlife. Their interment was an act of profound religious belief, but for us today, it was an act of incredible preservation. When archaeologists first uncovered the long, narrow pit and peered inside, they found a perfectly organized wooden puzzle. Hundreds of pieces, from massive planks of Lebanese cedar to delicate carved oars, were stacked in a precise, logical order, waiting to be understood. The reassembly of Khufu's ship was a monumental task in itself, a feat of modern archaeology that mirrored the ancient process of construction. For years, experts painstakingly fitted the pieces together, like solving the world's largest and most sacred jigsaw puzzle. And with every beam that clicked into place, a revolutionary truth became undeniable. There was not a single nail, no metal fasteners of any kind held this immense structure together. Instead, the entire hull was a complex web of interlocking parts, sewn and pegged with wood and rope. Here was the blueprint laid bare. The vessel's design was a masterpiece of flexibility. The planks were not rigidly fixed, but were connected with a system of mortise and tenon joints, which are like wooden tabs and slots, and then lashed with ropes made from papyrus and grass. This allowed the ship to twist and bend with the waves, to absorb stresses that would have shattered a rigid, nailed hull. The discovery proved that this was not a primitive method. It was a sophisticated, deliberate, and brilliantly engineered solution, one that created a ship capable of navigating both the calm Nile and the unpredictable open sea. The hull of Khufu's ship was a tapestry of tension, woven together not with metal, but with fiber. This was the core secret, a brilliant system of lashing that transformed individual planks into a single living structure. They did not simply tie a few ropes here and there. They engineered a complex web of continuous bindings that ran throughout the entire framework. Think of it not as tying a package, but as stitching a giant wooden garment. Each loop and pass of the rope distributed stress evenly across the hull, creating a perfect balance of tension and compression. When a wave struck, the force was absorbed and dissipated through this flexible network, rather than concentrating on a few rigid metal points. This is what gave the boat its legendary resilience, allowing it to twist and groan with the sea instead of fighting against it. The magic lay in the material itself. The ropes were meticulously crafted from the very reeds that line the Nile, primarily papyrus and halfa-grass. These were not weak, temporary cords. Artisans would twist and braid these fibers into incredibly strong, durable lines. Papyrus especially possesses a natural resilience. When wet, it becomes even more supple and tight, its fibers swelling to create an even tighter, self-sealing bind. This was a material that worked in harmony with the water, not in spite of it. The entire vessel was essentially a stitched masterpiece, a wooden shell held in a constant, gentle embrace by thousands of feet of rope. This adaptable strength meant the boat could endure the gentle currents of the river one day and the heaving swells of the Mediterranean the next. How could something held together by thread possibly be stronger than a nailed ship? The answer lies not in rigid permanence, but in intelligent flexibility. A nailed hull is stiff, and under immense pressure, something has to give, often with catastrophic results. But a lashed hull could move, could breathe with the waves, making it not weaker, but infinitely more adaptable to the unpredictable power of the open water. But a flexible hull needed planks that could bend without breaking. Egyptian shipwrights were not just builders, they were master material scientists, intimately familiar with the living properties of wood. They did not have access to vast forests of dense oak or tropical teak. Their entire boat-building empire was constructed from the trees that thrived along the Nile, primarily the acacia and the sycamore fig. These were not just random choices. They were brilliant selections based on the unique characteristics of each timber. Acacia wood is incredibly hard and resistant to water, a perfect quality for a vessel that would spend its life submerged. Its tight grain and natural oils helped it repel water and resist the worms that could destroy a hull. The sycamore fig, on the other hand, offered a different kind of strength. It was more flexible and easier to work, allowing shipwrights to shape it into the elegant curves of a hull. The true mastery, however, lay in how they prepared the timber. Felling a tree was just the beginning. To transform a straight, rigid log into a gracefully curved plank required a deep understanding of wood's behavior. They used techniques like soaking and controlled steaming. A plank would be immersed in water or exposed to hot, moist air for long periods. This process softened the wood's natural lignin, the glue that holds its fibers together. Once pliable, the shipwrights could carefully bend it into the precise shape needed for the boat's frame. They would then lash it into place, and as it dried, it would permanently hold that new, perfect curve. This method meant they could create a strong, complex hull from relatively short planks, all without needing complex joinery or a single metal fastening. They were not forcing nature to conform to their designs. They were working in harmony with it, understanding its limits and its potential, coaxing the very essence of the wood to become a seaworthy vessel. Yet the lashing alone could not have created such a perfect hull. The true structural genius lay hidden inside the seams, in a wood-to-wood connection that predates nails by millennia, the mortise and tenon joint. Picture a small, rectangular peg, a tenon, carved to project from the edge of a plank. Now imagine a matching slot, a mortise, carefully chiseled into the edge of the plank beside it. When fitted together, they created a tight, interlocking puzzle that held the hull's planks perfectly aligned, side by side. This was the hidden skeleton that gave the vessel its shape and lateral strength. The lashing ropes handled the longitudinal stress, the pulling and stretching along the boat's length, while these countless wooden joints prevented the planks from sliding past each other, creating an incredibly unified shell. But how did they achieve such precision with what we would consider primitive tools? They worked with copper chisels and stone mallets, tools that required immense skill and patience. A master shipwright would not simply hack at the wood. Each cut was a deliberate act, a careful removal of tiny slivers to create a mortise hole with walls that were nearly perfectly vertical and smooth. The tenon had to be shaped with equal care, its sides straight and its corners sharp, so it would fit with a satisfying, snug tap of a mallet. There was no room for a loose, sloppy fit. The joint had to be tight enough to hold the planks firmly together, yet not so tight that it risked splitting the precious cedar or acacia wood. This was not crude construction. It was a form of woodworking that demanded an artist's eye and a surgeon's steady hand. The result was a monocoque hull, a single load-bearing skin where every element, every plank, joint, and lashing shared the burden. It was a structure that was far greater than the sum of its parts, a flexible yet immensely strong vessel born from the perfect marriage of wood, rope, and human ingenuity. This entire system of interlocking wood and fiber culminated in a meticulous assembly line along the riverbank. The process began not with the hull, but with the keel, the backbone of the entire vessel. Master shipwrights would select the straightest, strongest timber for this central spine, laying it on wooden blocks to create a stable foundation. From this keel, the skeletal framework began to rise, a rib cage of carefully bent and shaped frames that define the boat's future form. Only then could the true artistry of the hull begin. Workers would bring the prepared planks, each one already carved with its precise set of mortise and tenon joints. They would fit these planks together, one by one, starting at the keel and working upwards. The sound of wooden mallets tapping tenons into their mortises would have filled the air, a rhythmic percussion of construction. Each new plank locked securely into its neighbor, building the shell from the bottom up in a seamless, growing puzzle. But this wooden puzzle was not yet complete. Once the shell was fully formed, the final, critical phase began. Using drills made of copper or hard stone, artisans would bore a series of carefully spaced holes along the outer edges of the planks. This was a moment of immense precision, as drilling too close to the edge risked splitting the precious wood. Then, teams of workers would take coils of strong papyrus rope and begin the lacing. They would thread the ropes through these holes, pulling each pass with steady, coordinated tension. Think of it as lacing up a giant wooden shoe, but one where every pull of the cord tightened the entire structure. This lacing process did more than just bind the planks. It actively tensioned the entire hull, pulling every joint tight and creating that perfect, flexible unity. The final result was a vessel that was not built to be rigid, but to be alive in the water. It could twist and groan, absorbing the energy of the waves instead of fighting it. A nailed ship resists the sea, but a lashed ship dances with it, a fundamental difference in philosophy that made these ancient boats so remarkably seaworthy. A vessel stitched together with rope presents an obvious question: how did it not simply sink? The genius of the Egyptian design extended beyond the wooden framework to the very seams that held it together. They perfected a waterproofing agent so effective it turned a network of potential leaks into a perfectly sealed hull. This was caulking, a sophisticated sealant made from a blend of natural materials. The primary ingredient was bitumen, a thick, tarry substance that we would recognize as asphalt. This was not a common mud. It was a valuable commodity traded from specific locations like the shores of the Dead Sea, where it naturally seeped to the surface. They would mix this sticky bitumen with plant fibers and tree resins to create a durable, pliable paste. The application process was a careful art. Workers would press this warm, malleable mixture deep into every seam between the planks, filling the gaps completely. As it cooled and hardened, it created a watertight gasket that was also slightly flexible. This meant that as the hull twisted and bent with the waves, the sealant could move with it without cracking or breaking away. But its purpose was twofold. This layer of caulking did more than just keep water out. It acted as a protective shield for the vital lashing ropes that lay just beneath the hull's surface. By preventing water from constantly soaking the papyrus fibers, the caulking drastically slowed down rot and decay. This single innovation extended the life of a vessel from a few seasons to many decades, ensuring that a pharaoh's trading ship or funeral barge would remain seaworthy for a lifetime. The bow was not just stitched, it was sealed, a perfect marriage of flexible structure and impermeable protection. With the hull sealed and ready, the true test of Egyptian ingenuity rose from its very center. A boat's ability to carry cargo meant nothing if it could not conquer the river's currents and the sea's unpredictable winds. The solution was a towering pillar of wood and woven fabric, a masterpiece of engineering that turned air into motion. The mast was the heart of this system, often a single massive trunk of cedar or acacia, selected for its straight grain and immense strength. This was not simply a pole jammed into the hull. It was a carefully integrated component, secured by the same philosophy of flexible lashing that defined the entire vessel. A massive forked timber called a crutch was lashed to the keel, cradling the base of the mast. From there, a web of heavy ropes, known as shrouds and stays, radiated outwards, anchoring the mast to the sides and ends of the boat. This network of tension transformed the entire hull into a single load-bearing unit. When the wind filled the sail, the force was not concentrated on one weak point. Instead, it was distributed evenly through these ropes, channeling the immense strain across the flexible lash framework. The hull itself became a shock absorber, groaning and giving just enough to prevent a catastrophic failure. The sail was the engine, a broad, square sheet woven from countless strips of papyrus or, for the finest vessels, sturdy linen. This was not a simple, flapping cloth. Its design was brilliantly pragmatic. The sail was hung from a long yardarm at the top and controlled by sheets, ropes attached to its lower corners. By adjusting these lines, sailors could catch the wind from different angles, allowing them to travel upriver against the current by tacking back and forth. The entire system, from the massive mast to the woven sail, operated without a single piece of metal. Every component, every connection, relied on the strength of wood, the tension of rope, and the brilliant foresight of its creators. This was a ship that did not fight the elements of wind and water, but one that was designed from the keel up to work in concert with them. Yet even with the wind as their primary engine, the Egyptians knew the river and sea were not always willing partners. For the calm days when the sails hung limp, and for the intricate maneuvers required in crowded ports or narrow channels, they developed a system of manual propulsion that was just as ingenious as the hull itself. Long, slender oars provided the power. These were not crude paddles, but carefully crafted levers, shaped from resilient woods like acacia to withstand constant stress and immersion. The real innovation, however, was not in the oar's blade, but in its point of contact with the boat, how you attach a moving oar to a flexible, lashed hull without tearing it apart. The answer lay in the oarlock, a deceptively simple device made entirely of wood and rope. A forked wooden bracket was securely lashed to the gunwale, the upper edge of the boat's side. This bracket cradled the oar, acting as a fulcrum. The oarsman would then secure his oar with a rope grommet, a loop that passed through a hole in the oar's shaft and was tied to the bracket. This system gave the oar a fixed pivot point while still allowing the rower to easily lift and reposition it. It was a perfect union of stability and freedom, all achieved with simple, durable materials. But directing this manually powered vessel required a different kind of control. At the stern, a single massive steering oar, often larger than a man, served as the ship's rudder. This was not a minor implement, it was a critical piece of equipment. To manage its immense size and leverage, it was mounted to a sturdy vertical post that rose from the deck. The oar was lashed to this post with heavy ropes, creating a pivot that allowed the helmsman to swing the entire blade from side to side. With a firm push or pull on the long handle, he could angle the oar deep into the water, guiding the ship's course with remarkable precision. Every part of this propulsion system, from the smallest oarlock to the great steering oar, was an extension of the boat's core philosophy. There were no metal pins, no rigid hinges. Just wood, rope, and brilliant design, all working in harmony to command the water. But could these theories truly hold water against the open ocean? The ultimate test did not come from a dusty papyrus scroll, but from the daring ambition of modern adventurers. In the 1960s and 70s, a Norwegian explorer named Thor Heyerdahl launched a series of radical experiments. He believed ancient civilizations could have made long ocean voyages, and he set out to prove it in the most dramatic way possible. He constructed a boat named Ra, built not from cedar, but from papyrus reeds, lashed together in the exact manner depicted on Egyptian tomb walls. With an international crew, he set sail from Africa, aiming to cross the Atlantic. The first attempt nearly succeeded, falling just short of its goal. But a second boat, Ra 2, built with refinements learned from the first, completed the journey, sailing from Morocco to Barbados. This was not a calm river cruise. This was a battle against towering waves and powerful storms. The papyrus boat, held together only by rope, demonstrated a remarkable quality. It flexed and twisted with the ocean, riding over waves that would have smashed a rigid hull to pieces. It did not simply survive the journey, it proved its design was inherently suited for the sea. These voyages were more than just stunts. They were living proof that the materials and methods of antiquity were not just for show. They were a functional, brilliant technology capable of feats we had long dismissed as impossible. Decades later, another project approached the question with even greater precision. The full-scale reconstruction of Khufu's solar boat in Egypt was a different kind of journey, one of meticulous craftsmanship rather than high-seas adventure. Using the same types of wood, the same copper tools, and the exact same lashed and pegged techniques, a team of dedicated shipwrights and archaeologists rebuilt the pharaoh's vessel from the ground up. This was experimental archaeology in its purest form. Every challenge the ancient builders faced, the modern team faced as well. They learned how the wood wanted to bend, how much tension the ropes could bear, and how the mortise and tenon joints snapped together to create an incredibly sturdy frame. The finished replica was not just a museum display, it was a functional boat, tested on the water and found to be perfectly stable and seaworthy. These two projects, one a bold Atlantic crossing and the other a careful reconstruction, reached the same undeniable conclusion. The Egyptian method was not a primitive compromise. It was a sophisticated and highly effective marine technology. These boats were not fragile river craft. They were ocean-going vessels, engineered for endurance, their flexibility a secret weapon against the raw power of the sea. This flexible, breathing hull was not just a clever workaround. It was a superior design, offering advantages that a rigid, nailed ship could never match. Think of a modern car's suspension, built to absorb the shocks and bumps of a rough road. A nailed boat is like a car with no suspension at all. Every wave is a direct, jarring impact, but the Egyptian boat, with its lashed planks and wooden joints, had a built-in suspension system for the sea. It could twist and groan, allowing the immense energy of a crashing wave to flow through and dissipate across its entire structure. This dramatically reduced the cumulative stress on the hull, preventing the fatigue and cracking that would eventually doom a brittle vessel. The boat did not fight the ocean, it danced with it, and in that dance lay its longevity. Material durability was another critical victory. The Mediterranean and Red Sea are saltwater environments, a corrosive nightmare for any metal. Iron nails, had they been widely used, would have rusted away, weakening their grip and staining the precious wood with destructive oxides. The Egyptian solution was perfectly adapted to its environment. Their ropes, made from papyrus and halfa grass, actually thrived when wet. The fibers would swell up, tightening their own knots and creating a self-sealing bind that grew stronger in the very element that threatened to destroy the ship. While a metal fastener was slowly being eaten away by the salt, the plant-based lashing was being maintained and reinforced by the water itself. This created a perfect cycle of preservation. The external layer of bitumen caulking kept most of the water out, protecting the ropes from constant rot, while the occasional soaking kept the fibers supple and strong. It was a brilliant, closed-loop system where every component supported the others. This nail-free approach was not a primitive step in our technological evolution. It was a sophisticated, purpose-built technology that understood its materials and its environment on a profound level. The Egyptians did not build this way because they had to. They built this way because, for their world, it was simply the best way. This vast fleet of ships required a nation of builders to sustain it. Shipbuilding in ancient Egypt was not a small-scale craft. It was a massive, state-sponsored industry that mobilized thousands of skilled hands. Think of the sprawling shipyards along the Nile, buzzing with coordinated activity. Teams of lumberjacks, armed with copper saws and stone axes, would venture to procure the precious cedar from Lebanon or the local acacia. Rope makers worked tirelessly, twisting and braiding miles of papyrus fiber into the strong cords that stitched the hulls together. Master shipwrights directed the assembly, while caulkers carefully sealed the seams with hot bitumen. This was an economic engine. a complex web of specialized labor that supported entire communities. The knowledge required for each step was not written in formal manuals. It was a living library passed directly from master to apprentice, from one generation to the next. A young boy would learn by watching, first by fetching tools, then by practicing simple cuts, and finally, after years of dedication, by carving the critical mortise and tenon joints himself. This oral and practical tradition was the only way to preserve the intricate nail-free techniques that define their craft. The state, understanding the strategic importance of these vessels, organized and funded the largest projects. When a pharaoh required a new fleet for a military campaign in the Levant, or when a massive funerary barge was needed for a royal tomb, the royal administration would commandeer materials and mobilize these skilled workforces from across the kingdom. It was this top-down support, combined with the bottom-up mastery of the craftsmen, that created a perfect ecosystem for preserving knowledge. The methods for building a flexible, lashed hull were simply too vital to ever be lost. They were the backbone of Egyptian power, commerce, and religion, ensuring this brilliant, nail-free technology endured, unchanged in its essential principles, for over 3,000 years. The true test of the Egyptian shipwright's art came not on the familiar Nile, but on the treacherous waters of the Red Sea. Here, the gentle river currents were replaced by powerful ocean swells and unpredictable monsoon wind. Yet Egyptian inscriptions boast of massive, state-sponsored expeditions sailing south to a fabled land known as Punt, a place of exotic incense, gold, and rare woods. For centuries, these accounts were thought to be exaggerated tales. Then, archaeologists uncovered the Wadi Gawasi shipyard. This is not a riverside dock, but a full-blown port facility on the Red Sea coast, complete of workshops, anchors, and storage caves. They found the remains of seagoing ships that had been disassembled after their long voyages, their components carefully stored for reuse. The discovery was definitive proof. The Egyptians were not just river sailors, they were deep-sea mariners. To conquer the open ocean, their vessels required crucial adaptations. The hulls needed to be stronger and deeper to handle the heaving seas. Shipwrights achieved this not by changing their core philosophy, but by refining it. They used thicker planks of cedar, tightened the lashing pattern to create a denser web of rope, and reinforced the internal framing. The sail configuration also evolved. While Nile boats often used a single, broad square sail, seagoing vessels likely employed a more versatile rig. A bipod mast, two legs forming an inverted V, provided greater stability against the fierce side winds of the Red Sea. This setup distributed the immense force of the wind more evenly across the flexible hull, preventing a catastrophic capsize. All of this, every reinforced joint and every new rope, was accomplished without a single nail. The voyages to Punt were journeys of over 1,000 miles, round trips that took many months. They were the ancient equivalent of a mission to another planet, a monumental undertaking that demanded absolute faith in the ships. The fact that they succeeded, repeatedly, using the same lashed and pegged techniques, is the ultimate testament to their system's genius. This was not a technology limited to a single environment. It was a robust and versatile philosophy of engineering, proven on the world's most challenging stages. These ships were more than just machines of commerce and war, they were vessels of the soul. The Egyptian worldview was built upon a cosmic river, a celestial Nile that flowed through the heavens. The sun god Ra did not simply blaze in the sky, he sailed across it each day in a magnificent solar bark, a divine boat that brought light and life to the world. This was not a distant myth, it was a daily reality that shaped their entire understanding of existence. And just as Ra sailed the sky, the deceased pharaoh, a god in his own right, needed his own bark to join this eternal journey after death. This is the profound reason why Khufu's solar boat was sealed in that pit at Giza. It was not a grand toy for the afterlife, it was a functional, sacred vehicle for the king's final and most important voyage. The boat's construction was therefore a spiritual act as much as a technical one. Every material used was chosen from the living world. The wood from the cedar tree, the ropes from the papyrus reed, the bitumen from the earth, these were all gifts of nature. They were organic, breathing substances that had once been alive, perfectly suited to carry the soul through the cycles of death and rebirth. A boat held together by metal nails would have been conceptually wrong, even blasphemous. Metal was mined from the dark, static earth. It was associated with weapons, with warfare, with the impermanent world of mankind. It did not belong in a vessel destined for the celestial realm. The flexible, lashed hull mirrored the flexibility of the spirit itself, capable of bending and adapting to the unknown currents of the afterlife. The entire boat was a prayer in physical form, a promise of renewal woven from the very fibers of the natural world, ensuring the king's journey would be as eternal as the rising and setting of the sun. So how did this Egyptian system stack up against the maritime giants of their day? Look across the Mediterranean to the Minoans of Crete, masters of the sea who built a vast trading empire. Their ships, sleek and fast, were held together with a different kind of ingenuity. They used thick, protruding tenons that locked through the planks, secured not with rope but with wooden dowels. It was a strong, rigid frame, a stark contrast to the flexible, woven hull of an Egyptian vessel. The Minoan method was brilliant, but it was a step toward a more permanent, fixed construction. Further east, the Phoenicians, perhaps the greatest sailors of the ancient world, took this evolution even further. Their legendary vessels, which traded from Britain to the Horn of Africa, began to incorporate metal fastenings. They used copper and later iron nails to clamp their hulls together, a technology that offered speed and strength but sacrificed that crucial ability to flex with the sea. And in Mesopotamia, the cradle of civilization between the Tigris and Euphrates, shipwrights worked with a material the Egyptians largely avoided for large ships, bitumen-coated baskets of reeds. Their boats were essentially floating waterproof baskets, effective for river trade but utterly unsuited for the open ocean voyages the Egyptians routinely undertook. This is the crucial distinction. While their neighbors were exploring the path of metal and rigid frames, Egypt was perfecting an organic alternative to a degree no one else matched. They did not ignore metal because they were primitive. They rejected it as a primary fastener because their entire engineering philosophy was built around flexibility. While a Phoenician ship resisted the waves with rigid strength, an Egyptian ship absorbed them, a fundamental difference in approach. Why did Egypt alone cling so fiercely to this rope and wood method? The answer lies in their unique geography and resources. The Nile was their lifeblood, a predictable highway that rarely demanded the brutal, rigid strength needed for constant Atlantic storms. Their materials, papyrus and acacia, were perfectly suited to this environment, creating a system that was not just effective, but perfectly sustainable for their world. They found an elegant solution and refined it over millennia, creating a maritime technology that was, in its own way, as advanced as any nailed hull on the high seas. The absence of iron did not mean an absence of precision. Egyptian shipwrights possessed a complete and highly effective toolkit, one that turned raw timber into elegant, seaworthy vessels. Their primary metal was copper, forged into saws, adzes, chisels, and drills. Copper is a soft metal, far softer than iron, and it would have dulled quickly against dense woods like cedar and acacia. This apparent weakness, however, was the very source of their ingenuity. A dull tool is a useless tool, so these artisans were in a constant, intimate dance with their materials. They could not afford to waste a single motion or make a sloppy cut. Every action had to be deliberate, every strike of the mallet measured. The copper chisel, for instance, was the key to creating the perfect mortise and tenon joints. A shipwright would hold the chisel against the wood and tap it with a stone mallet, peeling away tiny, controlled slivers. He was not cutting so much as he was coaxing the wood, feeling its grain and density with every movement. A heavy hand could split a priceless plank of Lebanese cedar, ruining weeks of work. This forced mindfulness resulted in joints of astonishing accuracy, with walls that were smooth and square, allowing the tenons to fit with a snug, satisfying tap. The limitations of their metal did not hinder their craft. It refined it, demanding a level of skill and patience that is almost unimaginable today. A freshly launched Egyptian trading vessel represented a massive investment of labor and materials, and its life was carefully managed to protect that investment. The operational life of a lashed boat could span several decades. a testament not only to its initial construction, but to a continuous cycle of maintenance. The flexible hull was designed to be serviced, not simply replaced. Over time, the constant flexing and the natural decay of organic materials meant that maintenance was a regular part of a sailor's life. The most common task was the retightening of the hull lashings. As the papyrus ropes dried and contracted, or as the wood itself settled, the perfect tension of the hull could loosen. Teams of workers would periodically inspect every seam, using simple wooden levers to carefully pull the ropes tighter before securing them with new knots. This was not a sign of weakness, it was the system working as intended. The boat was a living entity that needed its sinews tightened, much like a musician tuning the strings of an instrument to keep it in perfect harmony with the sea. The other crucial task was reapplying the bitumen caulking. The sun's heat and the water's action would slowly break down the sealant, creating tiny cracks. Workers would carefully scrape out the old, brittle material and press in a fresh, warm mixture of bitumen and resin, ensuring the hull remained watertight and the precious lashing ropes beneath stayed protected from rot. This regular upkeep meant a vessel could see 30, 40, or even 50 years of reliable service, a lifespan many modern boats would envy. When a ship finally reached the end of its seafaring days, when its timbers were too worn or damaged to justify further repair, it did not simply become waste. The Egyptian approach to resourcefulness extended to the boat's retirement. The vessel would be carefully dismantled in a process that mirrored its assembly, but in reverse. Every reusable component was salvaged. The long, straight planks of precious cedar were the most valuable, often being cut down and repurposed for furniture, smaller rivercraft, or architectural elements in homes and temples. Even the older ropes could be untwisted, their fibers used for stuffing or as kindling. This was a deeply sustainable cycle where nothing was wasted and the life of the materials was extended far beyond their original purpose. This stands in stark contrast to the fate of a nailed boat. When iron nails in a hull begin to rust, the failure is often hidden and catastrophic. The rust expands, splitting the wood from the inside out, and the fasteners themselves weaken until they snap under stress. A nailed boat might appear sound one day and disintegrate in a storm the next. The Egyptian lash boat, however, aged gracefully. Its failures were gradual and visible. A rope would fray, a seam would open. It gave clear warnings, allowing for repairs that kept it sailing for generations. Its entire life cycle, from the first lashing to its final dismantling, was a masterpiece of practical, enduring design. Yet the brilliance of this rope-bound system came with a demanding reality. Those same papyrus fibers that swelled tight in the water held a hidden vulnerability when exposed to the dry, baking sun. A boat pulled ashore for an extended period, its hull no longer cooled by the river, was at risk of a silent decay known as dry rot. The lashings, if allowed to cycle between wet and dry too frequently, could become brittle. Their inner fibers would weaken, losing the tensile strength that held the entire vessel together. This meant that Egyptian ships could not simply be built and forgotten. They demanded a relationship with their crew, a cycle of vigilant observation and hands-on care. A sailor's duties extended far beyond navigation. He was a mechanic, constantly feeling the tension of the ropes, inspecting the seams for signs of fraying, and watching for any subtle loosening in the hull's fit. A groaning, flexible hull was a sign of health, but a new, unsettling creak could signal a lashing on the verge of failure. This necessity for constant maintenance shaped their entire maritime culture. Long voyages required carrying spare coils of rope and pots of bitumen for emergency repairs. A sudden storm that stressed the hull might mean days of careful relashing once they reached calm waters. This was the inherent trade-off. The flexibility that gave them such resilience in rough seas also introduced a point of constant, meticulous upkeep that a rigid, nailed hull would not face. So when would this brilliant technique become a liability? Imagine a military campaign far from home, where a fleet needed to remain battle-ready for months on end, with limited time or resources for careful hull inspections. Or consider a culture whose ships were constantly in and out of the water, beached on harsh, sandy shores where the drying winds could quickly degrade the ropes. In these scenarios, the labor-intensive nature of the lashed hull could become a strategic weakness. It is no coincidence that as other civilizations advanced their metallurgy, making iron nails more abundant and reliable, they gradually abandoned lashing. A nailed ship could be built faster by less specialized laborers, and once launched, it required far less daily vigilance. Its strength was more static, more predictable for a commander who needed 100 identical warships ready for a specific campaign season. The Egyptian method was not replaced because it was inferior, but because it was perfectly optimized for a specific world, a world centered on the Nile and its rhythms. When that world changed, and when other priorities like speed of construction and low maintenance came to the fore, the age of the stitched ship naturally began to wane. The genius of Egyptian boat building refused to be confined by the sands of time. As their civilization waned, the principles they perfected began a quiet migration across the Mediterranean. We can trace echoes of their methods in the earliest Greek ships, the geometric period vessels that predated the classical triremes. These Greek boats also relied heavily on lashing to secure their hull planking, a technique that seems too similar to be pure coincidence. It was not a direct copy, but an adaptation of a core idea, the understanding that a hull bound by tension could withstand forces that would shatter a rigid frame. This concept of flexible strength became a foundational thread in the tapestry of early naval architecture. Even the mighty Romans, masters of engineering who built with concrete and iron, understood the value of this approach in certain contexts. Their smaller, regional trading vessels and fishing boats sometimes used lashing and wooden pegs, a testament to the method's enduring practicality for specific, everyday needs. The legacy was not in the exact replication of the Egyptian solar boat, but in the persistent idea that a ship could be a unified, breathing entity. This philosophy stood in stark contrast to the emerging paradigm of the nailed, rigid hull. For centuries, the two schools of thought existed in parallel, one favoring the permanence of metal and the other the resilience of fiber. The Egyptian solution proved that technological sophistication is not always measured by the hardness of your materials, but by the intelligence of your design. Their boats were a testament to working in harmony with natural forces, a lesson that resonates even in our own age of advanced composites and alloys. The most enduring solutions often emerge from a deep understanding of limitation, transforming apparent weaknesses into legendary strengths. A fragile papyrus raft is perhaps the most persistent image of Egyptian boats, a picture that completely misses the mark. These were not simple bundles of reeds tied together for a short river crossing. They were sophisticated wooden ships, engineered from the keel up with massive timbers of imported cedar and local acacia. The papyrus was used for the lashing ropes, the stitching that held the wooden planks together, not for the hull itself. This distinction is crucial. It is the difference between a simple log raft and a meticulously crafted wooden vessel designed for both river and sea. Another widespread belief is that these ships were confined to the calm waters of the Nile, utterly incapable of handling the open ocean. We have already journeyed with the archaeological evidence from Wadi Gawassis and the triumphant modern voyages of the raw reed ships. These were not river taxis. They were deep sea freighters, embarking on voyages of over 1,000 miles to the land of Punt, navigating the powerful currents and monsoon winds of the Red Sea with a confidence that speaks volumes about their seaworthiness. Some even argue that the nail-free method was a primitive stopgap, a technology they used only because they lacked better options. This could not be further from the truth. They had access to copper and bronze, metals they used expertly for tools, weapons, and jewelry. They consciously chose not to use metal fasteners because their lashed and pegged system offered superior performance for their needs. The flexible hull was not a compromise. It was a deliberate engineering advantage, providing a resilience in rough seas that a rigid, nailed frame could not match. The true genius of these naval engineers lies in this very choice. They saw the inherent strength in flexibility, the durability in organic materials, and they built a maritime tradition that dominated the ancient world for 3,000 years without a single nail. This is not a story of making do, but of mastering what they had to perfection. The ultimate challenge for these floating fortresses of wood and rope was a cargo that defied belief: granite blocks weighing 200 tons or more. These were not just heavy objects, they were entire geological formations destined to become the needle-like obelisks and the core stones of the grandest pyramids. Moving such a monolith from a remote quarry to a construction site hundreds of miles away seems almost impossible. Yet they did it repeatedly, and the secret lay in a specialized vessel that pushed their nail-free technology to its absolute limits: the colossal barge. Think of a single hull, massive though it may be, trying to support a 200-ton block. The concentrated weight would likely cause the entire flexible structure to buckle and fold. The solution was as brilliant as it was simple. They built gigantic barges by lashing multiple hulls together, side by side. This created an immensely wide and stable platform that distributed the stone's immense weight evenly across a vast area of the water's surface. It was the ancient equivalent of a modern heavy lift ship, a catamaran of monumental scale. Each individual hull was constructed with the same lashed and pegged techniques, but everything was reinforced. The planks were thicker, the lashing ropes were heavier and more densely woven, and the internal framing was a forest of timber designed to channel the loads downward. These were not graceful sailing ships, they were floating dry docks, powered by armies of rowers in dozens of small accompanying boats that would tow the barge along the Nile's current. The true engineering marvel was the loading process. How do you get a 200-ton stone from the riverbank onto the barge without cranes or hydraulics? The most plausible theory involves a feat of clever civil engineering. They likely dug a canal side channel right up to the quarry. The empty barge would be floated into this channel, and then the entrance would be temporarily sealed. Workers would then slowly divert water away, causing the barge to settle securely onto a prepared bed of mud and timber. The massive stone, already mounted on a sledge, could then be dragged directly onto the now stable barge using ropes, manpower, and the principles of leverage. Once the stone was perfectly centered, the canal would be reflooded, the barge would float free, and the journey could begin. This entire operation, from the multi-hull barge to the hydraulic loading dock, was a symphony of logistics that relied entirely on the strength and reliability of lash construction. A single failed rope under that kind of load would have been catastrophic, sinking both the stone and the barge in an instant. The fact that they succeeded not once, but for every single colossal stone in the pyramids, is the most powerful testament imaginable to the sheer capability of their nail-free boats. Their methods were not just adequate for the task, they were the only ones capable of achieving it. Every single lashing on that hull began its life as a humble reed, growing silently along the banks of the Nile. The entire system of flexible strength rested on the reliability of its ropes, transforming rope making from a simple chore into a high-stakes art form. The primary materials were papyrus and halfa grass, plants chosen not just for their abundance, but for their innate mechanical properties. Harvesting was the first careful step. Workers would gather the tall papyrus stalks, selecting only the strongest and most mature. They didn't just cut them down, they understood that the timing and part of the stalk mattered immensely for the final strength of the fiber. The outer green skin was often stripped away to reveal the tougher, more flexible inner pith. This pith was then beaten with mallets to separate the individual fibers, which were then soaked in water for days. This soaking was not just about cleaning, it was a crucial part of the process that activated the natural resins within the plant, making the fibers more pliable and sticky, ready to bind to one another. Once prepared, the real magic began. A rope maker would take a bundle of these damp fibers, and using a simple twisting technique, often rolling them against his thigh, he would create a single, tight strand. This was a skill that required immense feel and rhythm, applying just the right amount of tension to compact the fibers without snapping them, but a single strand was weak. The true strength came from combining these strands into a cord, and then twisting multiple cords together in the opposite direction to form a rope. This counter-twisting is the secret to all strong rope, as it locks the fibers in a state of constant balanced tension, preventing the whole thing from unraveling under a load. The rope maker had to maintain perfect, even tension throughout this entire process, as any weak spot or inconsistent twist would become a point of failure on the open sea. The final product was a masterpiece of tensile strength, a cable that could handle the immense forces exerted by a heavy sail or a flexing hull. This was not a haphazard bundle of reeds. It was a precision-engineered component, as vital to the ship's integrity as any timber. Every length of rope was a lifeline, and the ropemaker's craft ensured that lifeline would hold season after season. A master shipwright stands at the riverbank, a stack of acacia planks seasoned and ready. His first task is to transform these straight timbers into the curved ribs of the hull. He selects a thick plank and has his assistants build a small, contained fire nearby, not for burning, but for heating stones. They place these hot stones into a trough of water, creating a steady cloud of steam that envelops one end of the wood. For hours, they keep the wood bathed in this moist heat, slowly softening its natural resins. Once the fibers have relaxed, the shipwright and his team carefully bend the pliable wood around a curved form, lashing it securely. They leave it to dry and cool for days, and when the ropes are removed, the wood holds its new, permanent shape, a perfect rib for the boat's skeleton. With the frame set, the assembly of the shell begins. Workers bring over the long cedar planks for the hull, each one already prepared. Along the edge of the first plank, you can see a row of small, rectangular pegs, the tenons, carved to project outward. The corresponding plank has a matching set of slots, the mortises, chiseled with exquisite care. The shipwright aligns the two planks and gives a signal. His assistant taps the first tenon with a wooden mallet, and it slides snugly into its mortise with a solid thock. They move down the line, tap by tap, until the two planks are locked together in a seamless, continuous seam. This is repeated plank by plank, from the keel upward, the hull growing like a wooden tapestry woven directly on the frame. Now the true stitching begins. Another artisan arrives with a drill, a bow-driven tool with a copper tip. He positions it precisely and begins to rotate it back and forth, boring a clean hole through the overlapping edges of the joined planks. He works with practiced rhythm, creating a series of perfectly spaced holes along the entire seam. Then, the rope makers bring their coils of papyrus cable. Using a long, polished bone needle, they thread the rope through the first pair of holes, pulling it taut. They cross over and go through the next set, again pulling the rope tight. This is not a simple in-and-out stitch. It is a complex, continuous lacing that binds the entire hull in a unified web of tension. Teams work on both sides of the hull, their movements synchronized, their pulls evenly measured, until every seam is held in the constant, gentle embrace of the rope. With the hull fully lashed, the caulkers move in with their pots of warm, black bitumen. The mixture steams, giving off a sharp, tarry smell. Using wooden paddles and their hands protected by rags, they press the thick paste deep into every seam between the planks, smoothing it into a continuous, watertight seal. They work quickly before the bitumen cools and hardens, ensuring there are no gaps or bubbles. Once finished, the hull is transformed. The pale wood is now accented with dark, sinuous lines of sealant, a protective skin that will keep the water out and the lashings dry. Finally, the mast is raised. It is a massive trunk of cedar, hauled into position by dozens of men using ropes and sheer muscle. Its base is settled into the forked crutch secured to the keel. The rigging team swarms over the deck, lashing the heavy shrouds that run from the top of the mast to the sides of the boat, and the stays that run to the bow and stern. Each rope is tensioned, tested, and secured, transforming the flexible hull into a single load-bearing unit designed to channel the wind's power. The great square sail of woven linen is unfurled and attached to its yardarm, ready to catch the next breeze. From a pile of raw timber, a living, breathing vessel now sits ready on the water, a testament to the power of a simple, brilliant idea executed to perfection. From the sacred solar boats to the mighty trading vessels of the Red Sea, the story of Egyptian shipbuilding offers a powerful lesson for our own time. True innovation is not always about inventing something new, but about seeing the hidden potential in what already surrounds you. The Egyptians did not have access to limitless iron, so they turned to the reeds of the river and the trees of the valley, and they mastered them. They understood that the strength of a papyrus rope increases when wet. that cedar wood could be coaxed into perfect curves, and that a hull designed to flex would outlast one designed to resist. Their entire maritime empire was built on this profound principle, working in harmony with the properties of their world rather than fighting against them. This philosophy of intelligent adaptation connected their kingdom, fueled their economy, and allowed them to explore distant shores. So the next time you see a massive container ship or a sleek modern yacht, remember the ancient masters who proved that the most enduring bond is not always forged in a furnace. Sometimes, the strongest connection is the one you tie by hand, a knot pulled tight by human ingenuity and a deep, respectful understanding of the natural world.